Hi, everybody. And let's go to our websites and let's see. Okay, this is our schedule. And today is Friday, March 8th. Yeah, we behind schedule. It's okay. So today we will start 9.3. Okay, and then you have a spring break. After you are back, you have homework 6, which is about 9.1 and 9.2, and also quiz 3. So I hope over the break you're gonna work on your homework. Okay, so if you have questions, please come to see me and ask me. I know for some of the answer, they want you to express your answer in fraction times of pi. So then you have to put in fraction. If you put in decimals, they will mark you wrong. So yeah, be careful with that. So yes, and at the end of this week, I will enter your midterm grades. So I hope you can increase your homework scores and turn in the practice exams, exam correction, and wrappers. So that will increase your grades. Yes, I know some of you like turning the work. I haven't graded. I will grade it soon. Okay, so let's continue. So last time we talked about partial derivatives with respect to x and y. All right, and we were in so we did this example and we talked about the meaning, and we were in like second partial derivatives. Do you still remember? For if we only have two independent variables x and y, then we only have three different partial derivatives: fxx, fyy, and fxy, right? But if we have a function of three independent variables, well, then we have a first derivatives, there's like three of them, and the second derivatives, we're gonna have six of them, right, everybody? Let's continue. Okay. All right. So example 5, we have, this is f. Okay. Let's find all the first partial derivatives. And let's make it bigger. So fx. So this is the function. Partial f, partial x. We treat the x is the variable. And then we let the y and z be constants. Right? And when we take the derivative, you see, L and Z is like a number, right? Constant multiple just stays here. So we have L and Z just stays here. And then, ooh, see, this is like e to the u. What's e to the u derivative? Yes, times u prime. So e to the u is negative x squared y, right? And times u negative x squared y prime. And this prime is with respect to x. So far, so good, everybody? Okay. And now we continue and copy them. What is the derivative of negative x squared y? Yeah, very good. The y is just like a number. So negative 2xy. Okay. Is that okay, everybody? All right. So this is partial f, partial x. And let's look at partial f, partial y. Oh, what happened? Partial f, partial y. The first step is the same thing. L and z is like a number, and then derivative e to the u is e to the u times u prime. Our first step is the same. So we copy the first step. But then this prime means what? Yes. Right. So our second step will be different. Okay. Let me save some space. Yes, let's save some space and write tiny. Because you see there are so many things we need to consider for this problem. Okay, so write tiny. So L and Z, e to the negative x squared y. And what is the derivative with respect to y? Yeah, negative x squared. Okay, so this is partial f, partial y. So far, so good, everybody? Okay, partial f, partial z. So our first derivative. Okay, now x and y are constants. Z is the variable. Do you see e to the minus x squared y? It's like a number. So we copy it. E to the negative x squared y. And then we take the derivative. L and z derivative is, 1 over z. Very good. That okay, everybody? So this is the first partial derivatives. And this corresponds to the slope. Okay? Then you have your surface, right? You have a surface, and you can plug in different points in the partial derivatives. And if you get a positive number, it means if you're walking, so let's say partial f partial x is positive. It means you're walking along the positive x direction, and your function value is increasing, right? If your partial f partial y, when you plug in that point, is negative, it means if you're going along the positive y direction, your function value is increasing. That is what it means. Okay? The partial derivatives indicate whether the function is increasing or decreasing. The second derivative, okay? So remembering like how one, the second derivative corresponds to the concavity of the curve. If the second derivative is positive, you have concave up, right? And then that point is going to be a local minimum, right? If your second derivative is negative, your function is concave down. And then this guy would be the local maximum, right? Okay, so let's continue. So partial second derivatives now, right? We have fxx. Let's see. We need to take the derivative of this with respect to x. I would like to rewrite this better. Okay, I want to group all the negative 2xy and l and z together, and I want to put e to the negative x squared y. It's the same thing. I just changed the order because now we need to differentiate it. Okay, so let's use orange color. We differentiate. You can imagine is something times something is a product. So is a product. We use product rule. Everybody okay with that? Yeah, because if I use this form, it's like this times it's separated. I want to group them together. So now I'm only a product of two functions. So this is my first function. That's my second function. And what is product rule? U. So U V prime is exactly. Okay. Okay. So we have the U is the negative 2xy L and Z. Prime V v is e to the negative x squared y, and plus u. Oh, u, see? U is negative 2xy ln z times v prime. Okay, everybody? So the first step, we use product. U prime v plus u v prime. Now, continue. What's the derivative with respect to x? You see, all these numbers are like constants. The derivative of x is 1. Yes. So this is just negative 2y ln z. The derivative of x is 1. And the y and ln z, they're just number. Number stays here. Okay. E to the negative x squared y, and then minus 2xy ln z. So, okay, respect to x. Thank you. Now we see the derivative of this is e to the u times u prime, right? So e to the u times u prime, right? It's like the previous step. E to the u derivative is e to the u times u prime. And what's the u prime again? Negative 2xy, yes. Can I leave my answer like this instead of rewrite it and copy it again? So we can save some space. Hey, everybody. So that's the partial derivative, second partial derivative with respect to x. All right. Let's keep going. The next one is fyy. Fyy, we look at this guy. Do you see, maybe we can like move this in front so it's easier to see it that way. So we put negative x squared ln z times e to the negative x squared y. Yeah, move them together so it looks nicer. So when we take the derivative, do you see x squared is a number and z is a number, right? So they're just constant multiples. Do we need product rule? No, we don't need product rule. So it's constant multiple n times the derivative of e to the. Okay, so write it down. Then leave this here. And then the derivative of e to the u is what? Yeah, e to the u times u prime. But this prime is with respect to y, exactly. Which is negative x squared. Okay, nice. We can multiply them. Negative times negative becomes positive x squared times x squared. X to the fourth, ln z, and e to the negative x squared y. Is that okay, everybody? Yes. You gotta be very patient. Every step, ask yourself, what are the constants? What is the variable? And FZZ. Okay, FZZ. Ooh, so look at FZ. You take the derivative with respect to Z, right? This is like constant multiple, right? And this is what? Z to the. This is Z to the negative 1, right? When we differentiate, we make it to the standard form of a power function. And then we can use the power function rule. So the constant multiple stays here. What's the derivative of z to the minus 1? Negative 1 times z to the negative 2. Yes, yes, that's it. Right? X to the n, derivative is n times x to the n minus 1. Everybody? All right, good. We got fx, x, fy, y, fz. And then we need to do the next partial, right? Okay, let's see. We can do f, x, y. So let me use a different color. Yeah, it's a lot. Okay, f, x, y. And it equals to fyx. Okay. And let's see. We have two ways to compute. We either look at the fx and we take the derivative with respect to y, or we look at the fy and we take the derivative with respect to x. Which way do you prefer? The both of them we need product rule anyway. How about let's just use fxy. So we take the derivative of this with respect to y. Okay? And do you see this? The first step, the product rule is just the same thing. But instead of respect to x, respect to y now. So let's copy this whole thing here. Okay. So we have negative 2xy and z prime, but this is with respect to y, e to the negative x squared y minus 2xy and z, and then e to the negative x squared y, but then the prime is also with respect to y. When the problem get more and more complicated, we need to be patient and slow down. Every step, ask yourself, okay, this step, what am I doing? Okay, which one is the variable? Which one is the constant? And yeah, for a prospective student, I hope this won't scare you because you go to the upper level math class, the questions get more and more complicated. Okay, let's see. With respect to y, what's the derivative with respect to y? Yeah, negative 2x and z. The y just disappear times e to the negative x squared y and minus 2xy and z. How about the derivative e to the u? Yeah, e to the u times u prime. But what is the u prime here? Exactly, negative x squared. Is that okay, everybody? Mm-hmm. So if you rewrite again, okay, maybe let's rewrite again because looks like we can combine. Oops, sorry. Okay. Okay, where are we? Okay, here we're here. Sorry, I'm right-handed and the zoom in button is on the right side. I hope they put them on the left side. So yeah, I won't press that button by mistake a lot of times. Okay, so yep, this is negative 2x and z e to the minus x squared y, and we combine these two, we get plus 2x to the what? X, what power? We multiply them. Cube, yes. So y, l, and z, and e to the negative x squared y. So we just combine them and then it look better. All right. So far, so good, everybody. This is fxy, and we still have fxz. Let's see, fxz. Oh, this is better. By the way, mixed partial. This is the same as fzx. Okay, and let's see, fxz is you take the derivative of fx with respect to z. But the use of the z is much nicer because this is like a number, this is like a number. You only take the derivative of ln z, right? So we copy down minus 2xy and we copy down e to the minus x squared y. What's the derivative of ln z? 1 over z. This one is easy, right? Everybody? Okay, fyz and fzy. So fyz is the same as fzy. And look at the y, fy. Ooh. You see here? And this is a constant, this is a constant, and we just take the derivative of ln z. Is that okay, everybody? So that one is also easy. So minus x squared and e to the minus x squared y. What's the derivative of ln z? Yes, 1 over z. Okay. And this is all the second partial derivatives. Any questions? All good, everybody? Okay. So this is session 9.2. You just need to come down and review all the
So long.
yeah, it's so long, right? It depends on how complicated the problem is. Yes.
How many are going to be on that?
One problem.
One.
One problem. And I promise it will be easier than the practice exam one.
Okay.
The practice exam one, if you take a look, yes, your actual problem will be easier than the practice exam one. Okay, so yes, why do we learn second partial derivative? One main application is it can help us to find the maximum or minimum. Okay, so of a function with two and more variables. Okay, so local extreme. So functions of two variable has a local maximum, or you can say the relative maximum is just different name, but same thing. At AB, at the point AB, if f of xy is less than equal to f of AB whenever the xy is near it. So maximum, local maximum, it means this point is the highest point for the point near it. Okay? And local minimum is also called relative minimum if f of xy is greater or equal to f of AB, where xy is near AB. So this point is the local minimum. It is the lowest point for the points near it. Is that okay, everybody? Yeah, so same idea like we learned in Applied Power 1. Now just increase the dimensions. Okay, assuming that the partial derivatives are defined everywhere, how do we search for possible locations, A, B, where the local extremes can occur? Okay, so look at the picture.
Would this be considered three-dimensional?
Yes, this is three-dimensional, your
Yeah, because we're
XY.
looking at like cutting through.
Yeah, cutting through, right. And let's look at this. Imagine, let's say like we have, this is the x-axis and this is the y-axis and like this is the z-axis. Imagine like that. And you can see here the partial derivative with respect to x means your y is constant, right? Your y is constant. Then the picture is like you cut it and then you get this curve. Do you see at this curve your tangent line here, a tangent line is here. It's horizontal. Can you see a tangent line is horizontal? So it means your derivative with respect to x is 0. On the other hand, with respect to y means your x is a constant. So you have it like that. Do you see a curve is like this? And your slope of the tangent line. This is our one-dimensional picture. This is a two-dimensional picture. When you tell it, you can see the curve here. And then the tangent line is also horizontal. So the slope is also 0. Okay? Similar happen here. The partial x, see the tangent line horizontal. And the partial y, the tangent line is also horizontal. So this is a property we might have. Okay, partial f, partial x is 0. And partial f, partial y is also 0. So now for a function f whose partial derivatives are defined everywhere, the only possible locations for local extremes are those at which the partial f partial x is 0 and the partial f partial y is 0. And a point in the domain such that the first partials are 0, this point is called a critical point of the function. This is also similar to what we learned in applied cal 1, right? What's the critical point? When your first derivative is 0 or undefined. Okay. And if the first partial derivative exists, then the critical point means the derivative must be 0. Okay, be careful. Not all the critical points give local extreme maximum or minimum. A saddle point is a critical point, but it's neither a local max nor a local mean. Do you see this saddle point? If you look at the x, partial f, partial x is 0. If you look at the y, partial f, partial y is also 0. This is the saddle point. In the applied cal 1, right, we can have local min, we can have local max, and we can also have saddle points, right? But now, this is what a saddle point looks like in the surface. Cal 1. In applied cal 1, we're talking about a first dimension. Then local minimum looks like the local maximum. The x cube, like the x cube function, the derivative as 0. Derivative of x cube is 3x squared, right? When you put in 0, you get 0. But this critical point is not a local max or local mean. It's a set of points. Near the point, you have some point greater than that. You have some point less than that. So it's not a local max or local mean.
So even though it's dipping in between the two humps, it can't be a local minimum.
Look at this direction. So okay, if you look at the, so if you look at this direction, it's like that. But if you look at this direction, it looks this.
Yeah.
So that's why it's not a local max or local mean. Yeah, saddle point. Okay, note that the local extremas do not always come as isolated points. Yep, look at this function. Your local minimum is not a single point. It's the whole line. It is a local minimum. Is that okay, everybody? Yes. Okay, so now we just learned the second partial derivatives. Okay, and here all the second order partial derivatives of the function f can be collected in a 2x2 matrix on the Hessian matrix for f. Do you know what a matrix is? So you have rows and columns. And how we order them? Okay, it's the way that partial f, partial x, and then it's partial f, partial x, y, and partial f, partial y, x, and partial f, partial y, y. Okay, so this is the order how we write out the Hessian matrix. Fxx is in the 1 entry. Fyy is in the 2 entry. Sometimes you might get mixed up, oh, which is which. It turns out does not matter because the mixed partials, usually they are the same, right? So yes, keep this in mind. And yes, we have the theorem, the mixed partials. If the domain is an open set and the function partials are continuous, then we have the mixed partials equal. So in that case, the order fxy, fyx does not really matter. Okay, now let's compute the Hessian matrix. So we have the following function. We find fx. How about you guys take turns to tell me the answer? Okay, what is fx? What's the derivative of 3x to the 4?
It'll be 12x.
Yes. And then this one? And e to the y is like a constant.
Yeah.
So we get that. How about fy? Gabby? So fy, derivative of this is 0, right? Because x is now a number. And then derivative of the second term is yeah, we keep the 2x. Yes, very good. E to the y derivative is e to the y. Is that okay, everybody? Mm-hmm. All right. Now, what is fxx? Morgan. 36 x squared, and then oh, that's it. This has no x's at all. It's like a number. The derivative of a number is 0. Okay, yy is, let's see, we take the derivative with respect to y. The x is like a number, right? So it stays here. So 2x is like constant multiple, it stays here. The derivative of e to the y is 3 e to the y. Okay, how about fxy? And we know that's the same as fyx. Do you want to take the derivative of fx with respect to y or take the derivative of fy with respect to x? Up to you. Which way do you prefer? So this means we take the derivative of fx with respect to y. And this means we take the derivative of fy with respect to x. And it turns out they are the same. So you have 2 ways to compute this. How about let's take the first way. We take the derivative of this with respect to y. What's the derivative of the first term? With respect to y. So x is like a constant. What's the derivative of a constant? 0, yes. And the derivative of 2e to the y is, yes, 2e to the y. Is that okay, everybody? So this is one way to compute it. The second way is you look at fy, you took the derivative with respect to x. Do you see with respect to x, the derivative of x is 1? So you also get 2 e to the y. All right. Hessian matrix now. How do you put them? You put fxx here, so 36x squared. And you put the fyy there, which is 2x e to the y, right? And then you put fxy and fyx, they're the same thing. So which is 2e to the y. And this is 2e to the y. Is that okay, everybody? Good. Now, here comes the important parts. Second derivative test. Okay. This is the apply cal 1 second derivative test. Remember, second derivative corresponds to concavity of a function. If the second derivative is positive, concaves up, then this is a local minimum, right, everybody? If the second derivative is negative, the function concave down, and then this is a local maximum, right? And if the second derivative is 0, then the test is inconclusive. You have to find other ways to figure out whether it's local max or local min. Okay? Next part is, so that is for applying cal 1. Okay, this is about the curve and how about surfaces. So what we're talking about right now. Okay, the rule is consider the determinants of the matrix. Have you heard of determinant of the matrix? No. Okay, then don't worry about it. The formula is you do cross multiply. So fxx times fyy subtract fxy times fyx. So it becomes the same thing. So remember that is cross multiply, but you subtract. So fxx fyy subtract fxy squared. Okay, so this is the formula. D, we call this is the D. It means the determinant of the Hessian matrix. But if you haven't learned determinant, it's okay. Just think about cross multiply, but we subtract them, okay? Subtract. Okay. And now if AB is a critical point. Critical point means your first partial derivatives are 0. Okay. Once you find the critical point, you compute the following. You can put the points into your second partials, and then you get your D as a number. D. Imagine D. The effect of D is like your the second derivative. Okay. So if D is positive, then the graph of the quadratic approximation is a bowl shape. So it looks like a bowl. It either open up or open down. It looks like a bowl. If D less than 0, then the graph is like a saddle shape. Saddle shape. This is how I draw it, like saddle. Can you imagine saddle shape? Yes, saddle point. Right. If D is 0, then the surface, like the tangent plane, looks like a horizontal plane or a front shape. Front shape is like this. Okay? Or like a horizontal plane. Okay. Like this. Okay. So then we have the second derivative test for fxy. So a point is a critical point. Again, critical point means fx AB is 0 and fy AB is also 0. Okay, and then you compute all the D. Remember D is fxx fyy minus fxy squared. So if D is positive, think about it. This guy is positive, which means your first term is bigger. Right? Your first term is bigger. Your first term must be also positive. So if D is positive and fxx is positive, this will imply fyy is also positive. Does this make sense? D is positive. Oh, this guy is positive. Your first term must be positive because your second term is positive. You subtract some positive thing and you get a positive. Your first term must also be positive. And it's a bigger positive number than the second term. Right? And this is positive. And if fxx is positive, your fyy must be positive. Is that okay, everybody? What does that mean? Fxx positive. So in the x direction is gonna be concave up, right? In the x direction is concave up. And then fyy is positive. In the y direction is also concave up, right? Therefore, in all directions, the surface concave up, we get a local minimum. Yeah, concave up. Can you imagine? This is really like a bowl shape. Okay, in the x direction is concave up, in the y direction is also concave up, so it's a local minimum. Next, if D is positive, okay, D is positive, then the first term is also positive, right? But if fxx is negative, because the product is positive, one factor is negative, the other factor must be negative. Well, it means in the x direction is negative, so concave down. In the y direction is also negative, so concave down. Can you imagine? You get a bowl, but it's open down. Then that point is a local max. See from the picture, everybody? If D is negative, we get a saddle point. You can imagine, okay, in some direction, concave up, in some direction, concave down, so we get a saddle point. And the third one, if D is 0, the third test is inconclusive. You must find other ways to figure out whether it's local max or local mean. Other ways usually means you find more points near the critical point and plug in the F and compare the values. Is it bigger than that or less than that? Okay, so you pick like more numbers around it. Okay, and yeah, geometric meaning, I already talked about that. If D is positive and either the graph is concave out in all directions or the graph is concave down in all directions. It depends on your fxx. If it's positive, then fyy must be positive, all directions concave up. This is a local min. If fxx is negative, then it means all directions fyy is also negative. So we get concave down. This is a local max. And let's see. Yeah, that's why it's enough to just look at fxx to figure out the shape of the concavity. Okay? And if D is negative, it means some direction concave up, some direction concave down. It's a saddle point. So that's the theory of the second derivative test. Everybody understand so far? Okay, we learned long theory. Now, example. Yes, example. How do we do that? Okay, the first step is to find the critical points. So fx, fy. What is fx? Mackenzie. Derivative with respect to x is, yes, 4y. And the second term, y squared. Yeah, minus 2x. Very good. Right, everybody? Okay, and how about the derivative with respect to y? Well, oh, no problem. Sorry. Yes. Sometimes I'm very fast. Feel free to. Mm-hmm. Yes. Mm-hmm. Yeah, that's it. Right, everybody? The first step, we find fx, fy. A second step, we find the critical point. The critical point means set them equal to 0. Oh, a number. So derivative of a number is 0. Derivative of a constant. So you gotta be careful. If the number is multiplied by it, then it stays here. Because constant multiple. So like c times f prime is c times f prime. But if it's just c by itself, yeah, it will be 0. Right. Yeah, good point. Okay, so we set them equal to 0 and we solve for x and y. Okay, you get a system of equations. This part is hard. It's system of equations, and usually they're not linear. Remember questions?
Yeah, y is the second x, y squared again, minus the x squared. Fy.
Oh, fy?
It's
Here? Yeah, with respect to y. So with respect to y, 4x is like a number. The derivative of y is 1. And here, with respect to y, x is like a number. Oh, yeah. So it's 2xy. Thank you. See? Oh, okay. All right. Yes, so it's 2xy. Thank you. Yes. So we got to check our answer carefully. Because x is a number. X stays here. The derivative of y squared is 2.
You can move it too.
In f of x, why did x
Oh, because the derivative of x is 1. And then the y squared is like a number. Oh, okay. That is because when we take the derivative with respect to x, y is a number. Okay? Y is a number. So the derivative with respect to x, the derivative of x is 1. So you get 4y. 4y is a number, stays here. The derivative of x is 1. The y squared is a number, stays here. And then the derivative of x squared is 2x. That's with respect to x. Now with respect to y is a variable, x is a number. So 4x stays here. The derivative of y is 1. And then x is a number, stays here. The derivative of y squared is 2y. And then x squared is a number. The derivative of the number is 0. Yes. So we gotta really slow down and double check our answer before we continue. That's a really good point. Because if this is wrong, then everything after is all wrong. So gotta double check your setup. Okay, so when you solve system of equations, there are so many different methods, and usually we use the substitution method. Substitution is when you see in one of the equations, and then the variable you realize the power of it is 1. Okay? But in this case, the y, the power is 2. So don't look at this. But do you see the x, the power is 1? So we can solve for x in terms of y. And then we can plug in the second equation. You get an equation of 1 unknown. Okay? So substitution method.
This is why you said that.
And it also depends on the problem. Sometimes if you're not able to use substitution method, and maybe you're able to move all terms on one side and factor them, then you can set each factor equal to 0. So we will see more example. We will see those cases. Hopefully, I will explain what it means. So we compare. You see, x, the power is 1. We can solve for x. So we add 2x on both sides. We get 4y plus y squared is 2x. Right? And usually we should divide it by 2. But do you see here, we get 2x. So maybe you don't need to divide it by 2. Because 4x is what? 2 times 2x, right? So we can then plug in 2. Now 4x is like 2 times 2x. Yeah, 2 times 2x. And we know 2x is 4y plus y squared. Yeah. And then 2x. See, 2x is 4y plus y squared. And then times y. So this is what happens if we plug in the 2x is 4y plus y squared. Do you see we get an equation with only y in it? Next week, after next week, we will solve this equation. All right. Okay. So yeah, right now you can work on your homework about 9.1 and 9.2. And your exam 2 cover up to chapter 8 and 9.1 and 9.2. So over the spring break, you can start working on your practice exams. Okay. Happy spring break. Thank you. Yeah, increase your homework scores and the self-assessment scores. I will enter your midterm grade on Monday.